Okay. Okay, very well. Um, so we left each other the last time with the sample complexity lower bound for best arm identification. But since we did it in a very quick way, I will try to do a recap first of what we did, try to motivate why we are doing this, what are the main ideas, and then we move on from there. And today, if we can make it, we will start with the design of optimal algorithms. So the idea is that first we want to analyze the theoretical properties of the problem, try to analyze optimality, and then based on the results, we can come up with a design of what could be an optimal algorithm. So, so what we are doing is called pure exploration. So in pure exploration, you are a scientist, you are interacting with a system or a model, and what you want to do is to try to collect evidence. You want to collect evidence to come up with some conclusion about some underlying hypothesis. You want to test the efficacy of two drugs. You want to understand which drug is the best one. You're doing an hypothesis testing problem. And it's an active process because every time you observe new evidence, you will try to readjust your experiments based on what you have observed. So this is also called active testing or active learning because you are learning based on what you observe and you improve your approach. So there is a lot of notation, unfortunately, but here we represent a system by some parameter theta. So a system for us is a data generation mechanism, and you can see it here. So this p theta represents the distribution of what you observe. So the observation time t will be distributed according to some distribution p theta condition on all the past data. So this ht minus 1, you can see it here. It's the sequence of all the past data, the action in the first round, the observation in the first round, and so on. So based on all the previous interaction, you will observe a new observation when you choose what to do next. So you have a system. It's a sequential process. We denote each round by t. Okay, so t is the time step. So we start by t equal 1. In the first round, you choose which experiment to do. We also call experiments actions. So you choose which action to take. This is A1. You will observe X1 depending on some distribution p theta. Based on X1, you then decide which action to take next, A2. Then you will observe X2 and so on. So you have this sequence of observation. Every time you need to decide what to do next. And you also need to decide when to stop. When should we stop the data collection process? Depends if there is a fixed budget, or maybe you want to stop as soon as possible, as soon as you're confident that you can come up with a conclusion. So we also need a few more things. We also need an inference rule. The inference rule maps histories of data to decisions. So the decisions are it's like the space of hypothesis. And we assume that in this space of hypothesis, there is just one true decision that we can make, one true conclusion, one true hypothesis, call it as you prefer. So as you can imagine, the goal is to try to learn a way to choose the next action. We call this policy. So the policy maps histories of data, what you have observed so far, to an action. This delta A means the probability space over actions, because the policy can be a distribution over actions. It doesn't need to be deterministic. The inference rule, instead, we prefer it to be deterministic. And basically, it's a mapping from, this is HT, so from the history up to time t, to hypothesis. So based on all of this, we can also define a probability measure of the data we observe. We will denote it by p theta pi. This means that the data that we observed is influenced by this policy pi here and the parameter theta of the underlying model. And here pi, it's a sequence of policies. So it's not like just one policy. In each round, we can have a different policy. Okay. So I told you there are two objectives. One is the fixed budget. I give you a maximum number of rounds. And at the very end, I want you to make a prediction of what is the true hypothesis. So what you want to do here is try to come up with the best sampling rule, pi, and the best inference rule that allows you to maximize the probability of inferring the true hypothesis. So here the theta is the true hypothesis. This is your guess. We denote usually the guess is inferenced by the hat in the general case. Then when we look at the bandit problems, we will denote it by hat A. But this hat D is simply the output of the inference rule. Okay, so the inference rule maps histories to hypotheses or decisions, and we want the decision that we make at the very end to be correct as possible. The second case that we consider is the fixed confidence. So in the fixed confidence, there is a confidence parameter. Here, the goal is to try to stop as soon as possible, but we want to achieve also some level of confidence. So we need to introduce this parameter delta, that it's the confidence, it's like the error level. We also need to introduce a way to stop, a way to model the stopping. This is also called stopping rule, tau. It's a stopping time, so it's a random variable. And here, the problem that we are trying to solve is this infimum. So we are trying to minimize this average value of tau, so the average number of samples that we need, subject to a probability that the error will be at most delta. So here we are taking an infimum over all possible sampling rules, possible inference rules, possible stopping rules, and we want the average stopping to be minimized subject to this constraint on the error rate. Okay, so we want delta to be small, possibly, but obviously the smaller delta and the harder will be the problem. And here what's interesting is that the inference that we make, the hat tau, well, depends on tau. It depends on this random variable. So not only it depends on the trajectory that is random because of pi, and because of the underlying probability distributions of the model, but we also have the problem of that we have this stopping rule tau that can cause some problems. So this is the very general case. Now what we will do is try to look at a simple problem called the best arm identification bandit. Then from that, we will move on to best policy identification for MDPs, so Markov decision processes, which are a more complex model. And then in the very last lecture, we will come back to this full general problem and try to come up with a way to solve it using a different way, using techniques maybe like deep learning and so on. Yeah. The theta? This is a fixed problem. So the question is, what is this expectation E theta? If theta is a varying parameter or if it's fixed. So for now, it's fixed. So we consider a fixed problem, theta. It's fixed. In the Bayesian case, theta is not fixed, but we have a prior over thetas. But here we are not considering any prior. We just fix the theta, but in the last lecture, we will consider a prior over theta.
Quickly speaking, depends on theta, but then it allows pi either to tau depend. I guess you have to be independent.
Yeah, yeah. Okay, if it's clear so far, we can look at the best arm identification problem. So here what we are looking at, it's a model called multi-arm bandit. In multi-arm bandit, there are k actions. What you do is try to find the action with the highest reward. That's the problem. So the names comes from basically, I don't know if it's called slot machines in English. Yeah. So you want to find like the slot machine with the highest reward. So you have k different slot machines. Each one has a certain probability of success, and you want to find which one has the highest average success rate. So here, it's basically the same model. We have k actions. Upon choosing an action A, you observe a certain reward X, distributed according to p theta condition on A. Here, there is no conditioning on the past history because the model doesn't have memory. And we will also write it in this way. And the true decision here, it's the arm that maximizes the average reward. So here, X is the reward that is sampled from some distribution p theta A. And we will also call it A star theta. For Gaussians, we will work mostly with Gaussian distributions. This expected value will be equal to theta A. So theta parameterizes the mean values. We will fix the standard deviation to some fixed values. And so for us, theta will become the value, the mean, the vector of mean values. And lastly, we use this notation to denote our recommendation at time tau. So for this specific problem, we don't use D, but we use A, because A is the arm or action for this problem. And we are going to look just at the fixed confidence problem. So in the fixed confidence, we want to minimize the sample complexity subject to this constraint on the accuracy. The last time what we derived in the second part was try to derive the lower bound. And here we'll try to explain the main ideas. First of all, in every problem, you need to define sort of what is your objective. What is your event of interest? So your event of interest is you want to identify a certain arm. Here I wrote the complement, so the event that we don't identify the best arm. For this case, it's the same. You define the event of interest, then you can define the correctness objective. So the probability that this event will happen at most with probability delta. And then what you want to do is, how can you come up with an optimal strategy? The idea is that you want to compare the data you have observed so far with respect to an alternative model. So let's say you know theta. You know the true model. In reality, we don't know theta. Well, let's say you know theta. Okay. You observe data from this model. Now you ask yourself, okay, but is there an alternative model, lambda, that could have generated the same data? Is there another model where the likelihood of having observed this data is high? Because if there is, then how can you be so sure that it's really theta, the true model? So what you want to do is try to falsify that the data is coming from lambda, from this alternative model. So you want to rule out all these possible alternative models. And what's important here is that we are not just considering any alternative model. We are just considering alternative model where the best arm in those model is different. Because if the alternative model has the same best arm, it doesn't really matter because our objective is just to identify the best arm. So if the two models have the same best arm, I mean, there is really not much to test. Now, you want to test with models with different best arm, so different property here of the event, E, that we defined. And you want to see if there is this alternative model that could have generated the same data. So it's a model such that this event E, the way I defined it, is likely under the alternative distribution P lambda. But how do we quantify the amount of evidence? The idea is to use the log likelihood ratio. Why the log likelihood ratio, not something else? While it gives us nice properties, we can do many things with the log likelihood ratio, and it's quite natural way to measure evidence between two models. And as we will see, I mean, we will use it because it has many theoretical properties that we can use. So the log likelihood ratio quantifies the evidence to test between two models, theta lambda. And it can also be defined as the logarithm of the random Nicodim derivative in a formal way. The last time we saw how to derive this. But if you're not familiar with the random Nicodim derivative with this concept, probably you have already seen what is a likelihood. You can think of it like ratio of densities. So the numerator, we are basically computing the density of the data we have observed up to time t under the true model. And at the denominator, we are evaluating the density of the data under the alternative model. When we take expectation of this log likelihood ratio, we have also a very nice property called chain rule that allows us to write the expected value as a sum of the number of times we have chosen action A up to time tau times the KL divergence between the Gaussian of parameter theta A and the Gaussian of parameter lambda A. So this is the number of pools of arm A. And this is the KL divergence, which is a measure of how far the two distributions are. And we have also shown a lower bound on this quantity, d delta 1 minus delta, where d is the Bernoulli KL divergence. So this is another KL divergence, but for Bernoulli distribution. Bernoulli distributions, basically there is this parameter p that represents the probability of success or not. And this is roughly log 1 over delta. So this is very nice because from here we can derive the lower bound. We apply the idea of finding the worst model, the worst alternative model. So we take an infimum over lambda that belongs to this set of alternative models here. And what's also nice is that in this expression, we have this quantity. This quantity is the number of times we have selected arm A. We can optimize this quantity to try to minimize the sample complexity. So the idea is to introduce this change of variable. We call WA the expected number of times you have selected arm A up to time tau divided by the sample complexity. So expected value of tau. And when you do that, here we had the expected value of n tau and a tau, but expected value of n a tau is equal to WA times expected value of tau. So here we get WA, expected value of tau is not affected by the optimization here. So we have the optimization over the alternative models. We find the worst, but now we can also optimize the sampling rule because here it is WA. If you think of it, it's the sampling ratio of arm A. So it's the average number of times we selected arm A. So we can optimize this W over the simplex over K. And so we have come up here with basically our lower bound. We have that expected value of tau is lower bounded by T star, d delta 1 minus delta, where the inverse of T star is defined this way. So the inverse of T star is exactly this quantity. T star is also called characteristic time. The inverse is a sort of information ratio. And here, I will repeat myself, the W is the important thing. The W here represents the optimal static sampling rule, the optimal static proportion of times you should select the arms. So intuitively here, we are taking basically an expectation over the KL based on the Ws. So the Ws tells you how much you should sample each arm based on the fact how difficult it is to identify that arm. And this depends on the alternative models and the properties of the problem. So what will be interesting for us now is try to understand more what's going on here with this optimization, try to maybe approximate it, and derive some insights. But already from here, you can understand that we can try to design an algorithm that is optimal if we just sample according to the best W. Like if you were able to compute the W here in this optimization, then you can just apply this W, and ideally you should be able to quickly finish the problem. But you cannot compute this W because you don't know theta. So the idea when we will pass to the next part is that we will use the current estimate of the model instead of the true model. Okay. Okay. So this was the recap. If there is any question, no? Okay. All right. Okay. So what we will do now is try to analyze some of the properties of this quantity, understand how it can be optimized. Okay. And then we will give some approximations for the Gaussian case. So the first thing we want to do is understand what is this infimum over alternative models. Just as a reminder, this set of alternative models is defined in this way. So it's the set of models lambda such that the optimal arm in lambda is different from the optimal arm in theta. Without loss of generality, we also assume that the best arm in theta, it's the first one. We will use this ordering of the arms. So basically, we can rewrite the set of alternative models as the set of models where the best arm is different from arm one. But what is the best arm? The best arm is just the argmax over A of lambda A. So what we are asking is that there exists some action such that lambda A is bigger than lambda 1. So if that is the case, obviously lambda 1 cannot be optimal. So the optimal action is not arm 1. And you can show that this is also equal to the union over arms different from 1 of this set of models. So basically, we decompose the global set of alternative models, and we partitioned it into different sets of alternative models. So in each set here, we have that lambda, so arm A could be optimal. And we call it alt A theta. So using this decomposition, we can also rewrite our infimum of the objective that we had as a minimization over A different from 1, infimum over lambda prime such that lambda A bigger than lambda 1 of this quantity here. I'm going to use a different index, WB, KL, theta B, lambda B. The next step is to observe that the infimum over a set, it's always equal to the infimum over the closure of that set. So here we have an open set, but because of this property, we can write infimum over lambda prime such that lambda A is bigger than or equal to lambda 1. And at this point, just intuitively, if you look at this problem here, this constraint is only forcing you to have a value of lambda 8 that is bigger than lambda 1. But for all the other values, there is no constraint. So if you are trying to minimize it, since the KL is positive or non-negative, and the same for WB, then you can just choose lambda B to be equal to theta B for all the B's different from 1 and A. So let me repeat, since WB times KL, it's always non-negative, because the KL is non-negative and WB is a probability. And the constraint doesn't involve any arm except A and 1. You can always set all the other values of lambda equal to the same value of theta. So you can set lambda B equal to theta B for B different from 1 and A. So if this is not clear, just imagine that we have another term, like some arm B, okay? So we have this additional term, omega B, KL, theta B, lambda B. But lambda B can be set equal to theta B, right? Because it doesn't violate the constraint. So, and removing this term just minimizes the quantity. So you can simply set lambda B equal to theta B then, and you're minimizing it. Okay. Very good. The next thing that we want to see is that because of the convexity of the KL divergence, we can show that lambda 1 needs to be equal to lambda A of the optimal. So, because so imagine that this was not the case, and you had, for example, lambda A equal to lambda 1 plus epsilon. So in this second term here, we would have this quantity here. But since lambda 1 plus epsilon, since lambda 1 is also bigger than theta a, removing the epsilon can make this quantity just smaller. So if removing the epsilon can make this quantity just smaller, then it means that we can just let epsilon tend to 0, so we must have lambda equal to lambda 1 at the optimum. And you can show that the optimal point needs to satisfy it's equal to this. How do we show that? So we can just look at this function and take the derivatives. So we know that the optimal point is the same. We call it M. So now just take the derivative, use the fact that it's a Gaussian. So the KL of the Gaussian, it's simply theta 1 minus M squared divided by 2 sigma squared. And here the same, theta a minus M divided by 2 sigma squared. So you can take the derivative, set it equal to 0. And we find the middle point I showed you before. So from here, we find that M needs to be equal to this. So it's exactly equal to the expression I showed you before. Now, if you differentiate another time, you find that the second derivative is non-negative. So this is exactly the point that we want, since we are minimizing the problem. Okay, so we were here. We can show that at the optimal value, lambda a needs to be equal to lambda 1. So we use this property to try to find what is this optimal point. So we just replace these two quantities by M. So we look at the derivative of this function in M, and then we set the derivative equal to 0 to find what is this point. And this is exactly this convex combination, this weighted convex combination of theta and 1 and theta a based on the W's. And this is similar to the concept we also saw in the first lecture of the two drugs, where we were testing against the worst case scenario, where the two arms have the same probabilities. And we chose as probability this weighted average, if you remember from the first lecture. So this is exactly the same concept. And we are gonna indicate this quantity by A W theta, or I will omit the theta in some cases. And so at the very end, we have shown that the characteristic time, the inverse, it's also equal to supremum over W over the simplex minimum over A different from 1 of W1 times KL theta 1 MAW plus WA KL theta A MAW. So in this case, I will omit the theta because there is no need to be so explicit. All good? Yeah. So what's interesting here is that we are basically, what's this saying is that we are comparing arm 1 with arm A. So we are trying to compare the evidence that we collect from arm A compared to arm A, and we test against an alternative model that is MAW. And then we are taking the minimum over actions. So we are trying to find the worst arm that we need to test. But it's always a test compared to the best arm, right? So which second arm is like the closest to the best? Basically, that's what's really happening. You're testing if the second best arm is maybe the best. Yeah. So if it's all clear, there are a couple of properties now of this problem. So the first thing we can try to do is to show that at the optimal value, all these quantities are the same. But since maybe we can avoid that, I can just write it down. If there is time, we can do it later, then we have a break. So there are a couple of properties of this problem. So if we denote by W star the optimal solution, an optimal solution, then this stuff here, the solution is unique. So this is very, very important. So in the general case, W star is unique, but this is not always the case. Depends on the problem. There are problems where there is more structure, where it's not guaranteed that W is unique. You can have multiple optimal Ws. So it's very important that when you analyze the problem, you try to understand if there is just one W or if there are multiple optimal solutions. Another important thing is that the mapping from models to optimal solutions is continuous. This is another extremely important property that we will use in the derivation of the algorithm. And then you can also show that the optimal value of W star satisfies these inequalities. So this is interesting because, I mean, as you can expect, it will assign more probabilities to arms that have larger mean reward. But here it's not saying anything about W1. We just know that it will sample the second best arm with a probability that is larger than the probabilities of all the other arms. And this is exactly the same concept I told you before. We are testing the best arm with respect to all the other arms, and then we are checking which other arm is the worst case scenario. And usually the worst case scenario is always that the second best arm is maybe the best one. Imagine a problem where the best arm has maybe average value 0.9. The second best one has average value 0.89. If the standard deviation is 1, it will take you like a lot of samples before you understand that there is a 0.01 gap. So in the end, you're almost always testing between the first and the second best, depending on the problem that you have. So I think these are all the properties that we need. Yes, and also obviously the WSR are all strictly positive. Okay, I will not do the derivation of this because it's too long. Let's see if at the end of the lecture we still have time. But for now, I would like first, before the break, that we derive some approximations for the Gaussian case. So what do we want to do here? What we want to do is to understand if we can upper bound and lower bound the characteristic time. Why do we want to do this? Because the sample complexity is mainly characterized by the characteristic time. So we have this kind of inequality, right? Here, it should be the Bernoulli-Kerr divergence, but allow me to write just log 1 over delta. So understanding like a good upper bound, a good lower bound on T star gives you an idea of how many samples you need, okay? So we can start with the upper bound. And to derive the upper bound, we first need to simplify the expression here that we have. So if you remember the T star, yes, we have this quantity here. So I'm gonna rewrite it. Here we have the middle value. But now we use the fact that the KL of the Gaussian, we know how to compute it. So the KL here, it's just theta 1 minus MAW. But what is MAW? It's theta 1 W1 plus theta A WA divided by W1 plus WA, all squared divided by 2 sigma squared. And we also have the other term, this one. And we have exactly the same thing here. So here it's just some boring computations. So let's look at the first term. So here we can multiply theta 1 by W1 plus WA. So theta 1 W1 will cancel out with this theta 1 W1. We are left with theta 1 WA plus theta A WA. So basically we are left with theta 1 minus theta A squared times WA squared. And here we can do we can do the same. So here we have W1 WA squared divided by 2 sigma squared theta 1 minus theta A squared divided by W1 plus WA squared plus WA. And here we have W1 squared divided by 2 sigma squared theta A minus theta 1 squared divided by W1 plus WA squared. Okay, so this quantity are the same. We can simplify, right? Let's also call this theta 1 minus theta A, we call it delta A. It's the gap between the best arm and arm A. So we get W1 times WA times delta A squared. And what do we get here? We get WA plus W1 divided by WA plus W1 squared. So we have this simplification. And so the final expression, it's simply this one. Okay, so now that we have this simple expression, we can use it to play with it a little bit. So remember that is the inverse of T star. So if we manage to lower bound this quantity by A, then this means that T star is upper bounded by A. So how do we lower bound this? Well, we just need to make a smart choice of W. Because T star is taking the supremum of it over W, so we can just take any W. Doesn't need to be bad, because otherwise maybe we get an upper bound that it's too loose. We want to get something that it's still close. And what we can choose, it's a WA equal to 1 over delta A squared divided by a constant. And here this constant is the one that normalizes the WA, equal to 1 over sum of A different from 1 of W 1 over delta A squared. And if you're wondering, W1, it's just equal to 1 over delta 2 squared divided by C. Because delta 1 is equal to 0, so we cannot use that. We use the value for the second arm. So this choice might look a bit artificial, but I mean, if you have experience with this problem, you know that the complexity of the problem usually scales with a gap. So it's a good guess in general to use the inverse of the gap as a measure of complexity. If you think of the previous example, the gap between the first and second arm was 0.01. So when you do 1 over 0.01 squared, you get 10 to the power of 4. So roughly you need 10 to the power of 4 samples for that problem from before. Times you also need to take into account the standard deviation and the delta, but that's roughly the idea. Yeah. Yeah, I mean, you need to know the true model, if that's what you mean. Yeah, so the question is that how can we maybe compute this if we don't know the model? Yeah, I mean, we cannot if we don't know the true model, but it gives us intuition about how the complexity scales. Okay? We still don't know actually if this is loose or not, but we are going to show a lower bound on T star later that shows that this is a good guess. Okay? So when we plug in these values in the previous expression, so the previous expression was W1, WA divided by 2 sigma squared delta A squared divided by W1 plus WA. So if we plug in those values, so what we get is, 1 over 2 sigma squared c squared delta 2 squared delta a squared times delta a squared divided by, here we have W1 plus WA. W1 is 1 over delta 2 squared plus 1 over delta a squared. And here we have C. So here just we need to simplify. So we can simplify the C. We can simplify this delta a squared. Then also here we can simplify. So we get 2 sigma squared C delta 2 squared. Here at the numerator, we have delta 2 squared delta a squared divided by delta 2 squared plus delta a squared. So now we have this simplification. And here you can collect delta a squared at the denominator. So that you can simplify the delta a squared. Now, the minimum over A is achieved at A equal to 2. Because if you choose a larger action, the gap also gets larger because arm 2 is the second best. So for actions different from 2, the gap here will be larger, this will become smaller. And so you are actually maximizing. So it's minimized for action 2. For action 2 here we get 1. So here becomes this term becomes 1 over 2. So at the end we get 1 over 4, 1 over sigma squared and 1 over C, but C was 1 over the sum of the gaps, right? So here it will become 1 over sigma squared, and C was equal to this quantity. And so we have just shown that T star theta must be upper bounded by 4 sigma squared, sum over A different from 1 of 1 over the gap squared. So yes, the gaps can characterize the complexity. And now for the lower bound, the idea is a bit different, but we should apply the data processing inequality I showed you before. So now to derive the lower bound, we basically use the idea that we used originally to derive a lower bound on the sample complexity. So if you remember, the expected log likelihood was this term here. And we know that this is lower bounded by this Bernoulli-Kerr divergence. When we optimize lambda, we were taking an infimum, right? But now if we can choose any model lambda that we want. It just needs to be an alternative model, okay? So the moment we choose any other alternative model, we are choosing an easier model. And since it's easier, we get a different sample complexity. We get a looser lower bound. So for example, we can choose a model where lambda is equal to theta b for all b different from some arm A. And instead, in arm A, we set lambda A to be equal to theta 1 plus epsilon. So when we plug in this model, we just get So we get this inequality here, which is basically giving you a lower bound on the sample complexity of arm A. And since this holds for any strictly positive epsilon, you can let epsilon tend to 0. And so at the end, the lower bound of the number of times you should select arm A is this quantity here. Now you just apply the same concept to all arms A. So for each arm A, you derive a new confusing model, a new alternative model. And so when you take the sum over actions, this becomes the expected sample complexity, upper bounded by sum over A of the Bernoulli-Kerr divergence divided by KL theta A theta 1. But what is KL theta A theta 1? Since it's a Gaussian, it's theta A minus theta 1 squared divided by 2 sigma squared. And so at the end, yeah, here it's sum over actions different from 1. At the end, we get this Bernoulli-Kerr divergence divided by the gap squared. So we can see that here the lower bound on T star, it's 2 sigma squared sum over A different from 1 of 1 over delta A squared. But before the upper bound was the same, but with factor 4. So the only difference between the lower bound and the upper bound is a factor 2, which means that the solution that we derived before is approximately optimal. So we are approximately close to optimality. So let's take a break now. We can continue around 10, okay? Okay, shall we start? Yeah. Let's, so I want to try to avoid like the last time that I reached the very last minute. So I will try to cover like the main details, and hopefully there will be no need to rush. Okay, I don't think there is much more to say about the lower bound. I think we explained the main ideas. We derived an approximation, derived an idea, an intuition of what should be the optimal solution, for example, in the Gaussian case. And we also derived, I think, an intuition. We have an intuition now of what we should do, probably. We know that the W represents the optimal static sampling rule. So an idea could be, can we use this lower bound and just plug in the estimate of the model that we have? Use this estimate to compute the optimal W star, the optimal allocation, and then try to apply the allocation, sample from this allocation to decide what to do next. This is exactly what we are going to do. We are going to derive the properties of an algorithm called track and stop. So chapter 3, it's about the design of track and stop. Track and stop is an algorithm inspired by the lower bound, which means exactly what I just told you before. Inspired by the lower bound in the sense that we use our estimate at MT of the model. We're going to call it hat theta t to compute W star. Okay, we are going to call it W star of theta hat t to indicate the dependency on the model that we are using. This is the main idea, that we're going to use the lower bound to derive the sampling rule. So the sampling rule will somehow depend on this W. So you can think that the next action we're going to take is sampled from this vector of probabilities here, from this distribution over actions. But there are some issues, because this W star might be very different from the optimal one, depending on how well you estimated the model. If theta at t is very different from the true theta, you might end up with a W star that it's maybe very, very different from the true one, and you're gonna just waste a lot of samples before maybe you realize that something is going wrong, okay? So it's not only trying to follow what the lower bound tells you, but you also need to ensure that you are estimating the model sufficiently well in the meantime. So there is this trade-off between following what the lower bound tells you and estimating the model. So we will cover this idea. And then there is the problem of stopping. When do we stop? How can we guarantee the delta correctness at the stopping? The main idea here that we will use is to try to derive a super martingale. Super martingales have a nice property that on average they decrease. And there are some theorems that guarantee you that non-negative super martingales converge almost surely to a finite value. And you can use this property then to derive the delta correctness. The idea is that you try to build a super martingale, a non-negative one, that under theta, that is a super martingale under the true model. So if it's a super martingale, it means that it can only decrease. What's the likelihood that you have a spike? What's the likelihood that it has some large value? Usually this likelihood will be very small. This will represent the false error rate, so like a false positive rate. And we will use this to control the accuracy of the problem. So we will use this to control the error rate of track and stop. All right, so I think today we will just cover the first part about the sampling rule. Tomorrow we will cover the correctness and proving the sample complexity. So for the sampling rule, oh, okay. Yes. So for the sampling rule, we use what's called the seed tracking rule. So remember that we want to follow the lower bound, but at the same time, we want to ensure that we estimate the model well to avoid the problem that we are not using the right W star. The seed tracking rule is very simple. Simply ensure that each probability W is at least epsilon. So we define the clipped simplex delta epsilon k to be the set of allocations over arms such that the minimum over A, WA is at least epsilon. So why it is guarantees that we can estimate the model well. The idea comes from Borel-Cantelli. Let me change color. So there is the second lemma of Borel-Cantelli. Here we use the conditioned one, which says, suppose that you have a sequence of random variables here, where each EI is Fi measurable. if the sum over the probability of EI given Fi minus 1 is infinite, then you also have that the probability of lim sup I EI is equal to 1. So now let's say we choose EI to be the event that in round T, or here we use I, so that in round I, we choose arm A. So what is the probability here that in round I, we choose arm A? So Fi minus 1, it's all the data we have observed so far. But if we constrain the Ws to belong to this set, and then we sample the arm according to any W from this set, we know that the minimum probability is epsilon. So the sum over I of these probabilities here, it's at least lower bounded by sum over I of epsilon. And here I goes from 0 to T. So as T goes to infinity, this also goes to infinity. So this means that arm A is chosen infinitely often. So this lim sup means simply that this event here is happening an infinite number of times, infinitely often. So if it's happening infinitely often, it also means that we are choosing arm A infinitely often, which means that we can show that we can estimate well the mean value of arm A by the law of large numbers. So I see some faces a bit, yeah. Yeah, we're gonna choose epsilon decay now. This is just to introduce the idea. In the end, we're not gonna use this. We are actually gonna use this result for MDPs, but for bandits, we are gonna use a different thing. But this is just an intuition of why setting a minimum threshold on the probabilities can help with the estimation. Because this guarantees that the number of times you have selected arm A tends to infinity, and by the law of large number, you can show that your estimate of theta hat AT goes to theta A. And since I'm already here, I can give also the definition of what is hat theta AT. It's simply the average value for Gaussians. So this is 1 over number of times we selected arm A up to time t, sum from n equal to 1 to t of the random variables we observed in round n times the indicator function that we selected arm A in that round. So this is just the mean value of arm A. And this will converge to theta A. Okay, so the tracking rule that we are gonna use, it's called C tracking, and it's defined in this way. So in this tracking rule, we have this quantity, and this quantity it's the projection on delta E and K of W A star of theta hat n. So we have our model estimated in round n, we compute the lower bound, we derive what is the optimal W for that model. Then we make a projection on the clipped simplex. And note here that the epsilon is not constant, it will decay. We will choose epsilon n to be equal to 1 over 2 square root k squared plus n. And so we do the projection. And so we can guarantee that the minimum value of WA here, it's at least bigger than or equal to epsilon n. What this sampling rule is doing is just trying to select the arm that has been undersampled the most compared to what the allocation tells you here. So here you are summing over all the rounds, the W that you computed, and then you take a difference with respect to the number of times you selected the arm. So if this quantity here tells you that you should have selected arm A, I don't know, 10 times, but NA is equal to 1, then probably you should sample that arm because you have been undersampling. We also choose the decaying epsilon so that in the limit, WA will converge to the true W star as theta hat converges to the true theta. So this is a reasonable choice. There are also other choices for the tracking rule, but this is a simple one. And it's also, I think, quite intuitive, I believe. So what we are going to do now is try to derive some properties of this sampling rule and use this property so we want to derive some properties that will allow us to derive this result. So what we want to show is that in the limit, the average fraction of times we select an arm will converge to the true WA star. So this is exactly the idea that in the limit, as we estimate the model more and more accurately, in the limit, we will converge to sampling according to the optimal static sampling rule W star. So this is the result we want to guarantee. What we want to show is that we can control this difference here somehow. And once we manage to control that difference, then we can easily show also this result. So for trying to control this difference here, we need first another proposition. I will not prove it, but I will write it here. So suppose to have a sequence of distributions over the simplex. We're going to call this distribution Q. And then we denote by PT the sum from 1 to n of these distributions from 1 to t. These are like vectors, right? So you can think of a sum of vectors. Then we define this sampling rule. So this has exactly the same form of C tracking. If you see, this PA T plus 1 is a sum of distributions. We have the difference with the number of times we selected arm A. Here we have the action selection. So if the action is selected in this way, then we can guarantee that the maximum over A of PAT minus NAT is upper bounded by K minus 1. Okay, very well. But what we want to control is how different is the average sampling rate to the true W star, not the W that we project. Okay. Here, P, basically it's this sum of the projected W. But what we really want to show is that we can control the difference with respect to the true W star. Okay. So the result we are going to show now is this one, lemma. So what we are going to show is that the number of times we sample arm A is lower bounded by square root T. Yeah. Sorry? Yeah. Okay, so the yellow thing here, it's saying that, so this PA is a sum of distributions, and this corresponds to the sum of the W epsilon that we have in C tracking. Okay? And what this saying is that you can control this difference, and it's upper bounded by K minus 1. So if you follow this sampling rule, then NA will be close to PAT. But we don't want to control this difference. What we want to control is how different we are with respect to the true W star, not the projected one. Okay? So what we're going to show is that first, each arm is sampled at the rate square root T. And secondly, max over A of NA T minus sum from n equals 0 to T minus 1 W A star hat A n. All of this is upper bounded by K times 1 plus square root T. Okay, so we can start by using the result in yellow. So we can apply it to the C tracking. So here what we are going to do is we are looking at this difference. So here we have star theta hat n, and we are going to do plus minus sum and from 0 to T minus 1 of W A epsilon n hat theta n. So we know that this quantity here minus NAT, it's upper bounded by K minus 1. So we can apply the triangle inequality here to get K minus 1 plus sum. Here we have an absolute value, W A star theta hat n minus W A epsilon n at theta n. We can also show that we can upper bound the difference between the W star and the W epsilon. So since each arm needs to be at least epsilon n, this difference can be at most k minus 1 epsilon n. We are going to write k epsilon n for simplicity. And because of the sum, then the upper bound on this quantity here becomes k minus 1 plus sum from n equal to 0 to t minus 1 of epsilon n. So now we have the problem of bounding this sum, and we are going to use an integral bound. I always forget this one, so I'm going to rederive it. So we have a monotonic decreasing function, okay? So let's say this is our function, f of x. This is point n, this is point n plus 1. So when you look at the integral of f of x, and you integrate between n and n plus 1, it's simply the area under the curve here. But this area is smaller than f of n. And similarly, you can also show that f of n plus 1 is smaller than this quantity here. So now, if we take the sum, so we do f1 plus up to ft plus 1. So f1, it's upper bounded by the integral from 0 to 1. f2, it's upper bounded by the integral from 1 to 2, and so on, up to integral from t to t plus 1. And this integral here, it's integral from 0 to t plus 1, and it's upper bounded. So the first term, it's upper bounded by f of 0, and so on, up to f of t. So basically, we have just shown that the sum from 1 to t plus 1 of f of n, it's smaller than the integral from 0 to t plus 1 of f of x dx, which is smaller than the sum from 0 to t of f of n. So I hope I got it right. I think it's right. So we wanted to show an upper bound and a lower bound on this guy here. So we can show a lower bound, for example, by considering this direction here. So this is our sum, and we want to lower bound it with an integral. And instead, for upper bounding this term, we consider instead this direction here. Okay. So the upper bound is simply going to be integral from minus 1 to t minus 1 of epsilon n, but epsilon n is simply 1 over 2 square root k squared plus, let's use x here. So we are integrating over dx. And So here it's simply the derivative of k squared plus x evaluated between -1 and t minus 1. And so we obtain square root k squared plus t minus 1 minus square root of k squared minus 1. And since we are already here, we can also do the lower bound. For the lower bound, we are gonna instead consider the other direction. Which is gonna be integral from 0 to t of 1 over 2 square root k squared plus x dx. So we get square root of k squared plus t minus k. Because it's exactly the same integral. So we have we have just shown that this difference, so difference from n equal to 0 to t minus 1 of w a star hat theta n minus n hat, it's in absolute value upper bounded by k minus 1 plus k times this upper bound on the sum, which is square root of k squared plus t minus 1 minus k squared minus 1. Now we can do a simplification that we can get rid of this minus simply using that square root of a plus b is smaller than square root of a plus square root of b if we have non-negative terms. So here we get square root of k squared minus 1 plus square root of t. So this k squared minus 1 here will cancel out with this one. And so at the end, our upper bound is k minus 1 plus k times square root of t. And so we can just write k1 plus square root t. So this was one of the two results we wanted to show, that this difference here in absolute value, it's upper bounded by this quantity here. So why is this important? Because now if you divide by t, if you divide this quantity by t, then this becomes like a sort of average difference. And this quantity here on the right, the upper bound, when you divide it by t, it will go to 0 asymptotically. So what this means is that asymptotically, the average difference will go to 0, which is what we want. The other results I wanted to show was the lower bound on A and AT. Yes. So the other results, we need to consider this difference here. So the difference that we have in C tracking. So basically, we go back to the first step of the proof, where we apply the proposition I wrote in yellow from before that told us that this difference is upper bounded by k minus 1. So if you go directly to the first step of the proof, we are basically back here. We are applying this. So we know that this holds in absolute value, which also means that this difference here holds. So we remove the absolute value, and we know that this difference is bigger than 1 minus k, which also means that NAT, it's lower bounded by 1 minus k plus the sum of the W projected on the clipped simplex. But each WA is lower bounded by epsilon n. And we should before the lower bound, right? What was the lower bound? The lower bound was like square root k squared plus t minus k. So we have 1 minus k plus square root k squared plus t minus k, which shows that the lower bound scales in square root t. So as t grows to infinity, then also the number of times you select each arm tends to infinity, which is also what we showed before with the Borel-Cantelli lemma. Yeah, I think we can also show the very last results for today. So the thing that we wanted to prove, that on average, our average sample rate will converge to W star. Because so far we have not showed that. We have just showed that there is this upper bound on the difference here. So on average, this will be smaller than this quantity divided by t. So we're going to use that now. So we have just showed that this difference, so now we have the W star. It's upper bounded in absolute value by k times 1 plus square root t. So when you divide by 1 over t, then this right-hand side will go to 0 as t goes to infinity. So now if you write NAT divided by t as 1 over t, sum from 0 to t minus 1 of WA star theta hat n plus NAT minus 1 over t. So I just did plus minus the sum from 0 to 1 of WA star. So in the limit, we know that this goes to 0. So what does this quantity converge to? And we will have our answer. So here we are going to use what we call the Cesaro lemma. It's a simple but important result. So here we have a sequence. So the Cesaro lemma says, consider two sequences, an, bn, such that the absolute value of bn tends to infinity, and bn is strictly monotone. Then, if the limit of the ratios between n plus 1 minus an and bn plus 1 minus bn converges to some quantity L, then we also have that the limit for n that goes to infinity of an divided by bn is equal to L. So we are going to apply it here to this quantity here. So we can think of t as the bn term. And the sum is the an term. So we're going to set at to be the sum from n equal to 0 to t minus 1 of wa star at theta n. And bt, it's simply t. So when we do at plus 1 minus at divided by bt plus 1 minus bt, what we get, it's simply wa star hat theta t. We know that NAT will tend to infinity. We also know by the law of large numbers that because of this, hat theta t will converge to theta. And we also know that the optimal location is continuous in the model. So by continuity, we can say that wa star hat theta t will converge to wa star theta with probability 1. So because of the Cesaro lemma, we have just showed that this quantity converges to wa star theta with probability 1, which is what we wanted to show. So our statement is that under the C-tracking rule, we are converging to the optimal location. So that's all for today. I mean, this result is not like extraordinary, but I think it shows you some of the tools that we use in probability theory, like the Cesaro lemma, try to reason about convergence and so on. Also the idea of sampling according to a distribution, try to derive a lower bound on the number of times you selected an action. So these are all useful ideas, I think, also in other fields, in other applications. So what we're gonna do tomorrow is move on from here. What we really need to show now is try to come up with a stopping rule. So use the martingale idea. That will be a bit cumbersome with the computations, but it's a useful exercise. And once we have that, we have the sampling rule, we have the stopping rule. We just need to show that asymptotically the sample complexity is optimal. So if there is no question, I think that's all for today. Thank you.